No.
Yeah, I did some stats of this year's SOAR program, the acceptances. I compared it to last year, just to see if there was anything interesting. Next slide. Yeah. So SOAR was made in 2025, summer 2025, after a conversation we had in off topic about the rise of open science labs. Eleuterii has been around since 2020. They've been doing a lot of LLM research, a lot of like safety stuff, like interpretability, just a lot of stuff related to large language models, essentially. So was created so we can get more people back here to just do projects, essentially. Because back then we had a lot of people doing projects, and it's an easy way to get people here, essentially. Next slide. Uh, this year and last year had the same type of projects. I guess this year we had some interesting AI for science projects. I don't think we had that last year. Last year we had two data entry projects. This year we didn't have any. I expect that to be the norm going forward. I don't expect there to be like any simple data entry aspect projects. I think this year the projects were in a lot stronger state. Like they joined with like half completed, like in a half completed state, for example. We got a lot more mentors this year as well, both in the sense of mentors that applied and mentors that got rejected. I think one important thing is I think a lot of the rejects were because the projects were just bad, like it was AI psychosis. So we had to reject a lot of them for being psychosis. The rest of the people who got rejected were just too inexperienced to be mentors. Next slide. Right. So this year we had 2.1% accepted. Last year we had 30%. I think because last year so was very hectic because we started planning everything like in the summer. So we didn't really have much time to like filter. We didn't have much time to like home applications, burn-ins, interviews. So there were a lot more people that got in last year. But this year, because of all of that, we got a lot more rejects early on. I think also the lower percent was just because there was a lot of spam, like a lot of AI generated applications. I'm not sure why that happened. Also last year, one project had like 50 people and it took in all. It went really well for them, but this year we didn't get that. I guess this year more of the mentors wanted like less people, more highly skilled people, I guess. Next slide. The drop rates. So, sorry about this. Last year, 41% of the people that accepted and got in just left the projects. So that means that 59% of the people that got in stayed through the entire course. We don't have any data for this year drop rates as yet. I'm only aware of like, I think like 5 people that dropped out so far.
Yeah, I think just
So
five.
yeah, I don't think we have that much. Like compared to last year, which was quite a lot of people. The next slide. Uh, there wasn't really any good demographic that really was standing out to me stats wise. So I just did education level. Uh, the acceptance seems around the same of last year, especially if you compare it with the amount of people that got in last year. I think it's double last year compared to this year. It's 14 times more difficult this year to get in. Oh yeah, the education question was kind of weird because some people had taken it to mean if it's their highest level of education rather than their current. So we had some of the high schoolers who were actually starting college. Some of the bachelors had left the bachelors a very long time ago and were essentially industry practitioners at this point. So yeah, that was kind of a problem. Next slide. Oh yeah, this is a bar graph of the applicants and the accepted by the education level. I don't think there's anything interesting this year. I guess it's just very hard to get in, no matter who you are. I can't I can't really give any good advice for how to get in because each of the mentors wanted something different from the applicants. So like once you're past the slop filter, like I really can't give you more advice than that because every mentor wanted something different. So yeah, next slide. Oh yeah, for the projects, I think this time around the projects are going really well. Like I think last year, I think around this time, most projects had like a proof of concept, some early code. I think this year we have a lot of projects just much further on. Because for some context, last year a lot of the projects went on after SOAR to be done at like a slower pace, just to like get out a paper, for example. But I think this year, I think one project is already like in a paper state, like it's being written up already. So yeah, I think this year it's really good.
Yeah,
Two projects
for
funding
the
as
other
well.
projects, that particular project also started uh, a bit before the actual SOAR, so you don't need to feel bad about not having a full paper yet.
Yeah, don't feel bad. I think it's just because a lot of people joined with like half finished projects already, and they did a lot of stuff before SOAR. So yeah. Next slide. Yeah, the other demographics like gender, country, it was mostly the same. I couldn't really find anything interesting. The skill set was as important as background and being accepted, but again, every mentor wanted something different. I really can't give good advice on how to get in. Every mentor wanted something different in their mentees. Next slide. Oh, yes. So, for some context, even though SOAR is meant to have only mentees from the applicants, each of the mentors sometimes bring in applicants not from SOAR. Like, I think last year, one person joined very late for my project, and I just let them in. I think there was like five in total last year, but I think this year there's a lot more people who are non-SOAR helping with projects. I think that comes down to a lot of the projects being in half finished state and they were just like they knew people beforehand before coming here essentially. So yeah. Next slide. Oh yeah, this is important. So because of the short amount of time last year, we didn't really get like it was much more harder to look at the mentees and stuff, but this year we did two things because of the sheer amount of applicants. I think we got like 3,000 this year, was it?
Yeah, so we went from
Uh,
500 last year to 3,500.
yeah. So all the managers, that would be us, we did a first filter before we gave them to the mentors. But the mentors were able to see all of the applicants that applied to them. Like I think the first project had like what 1,500 applicants. It's able to see all of them if they wanted to. And more importantly, we created a script so we can have like a web page view. So it's a lot easier for the mentors and for us to just look at the projects. It turns the spreadsheet into like a web page view so you can just see everything on like one file. It's much easier for everyone to work with compared to last year.
Yeah,
It's a lot easier UI, UX wise, yeah.
yeah. So
Uh,
mentees don't know that, but basically all of the applications live on a Google Sheet, and last year we
oh
just had the
yes.
Google Sheet view, which was not optimal. So, but that
Yeah.
not too much for your concern.
Yeah, this year there was a lot better UI UX to help with the. We had to do this because of the large amount of applicants. Yeah. Next slide, I think. Yeah. Overall, was just better this year. Like project wise, it was better. we had more time to do stuff. I think last year we had like what 1 or 2 weeks to look at the mentees applicants. I think this year we had like a little over 1 month, which was much better. Well, no, not 1 month. I think it was 2 months because of the early applications. I don't think there was much changes in demographics unless you want me to start hacking. Yeah, just because of the larger timeline this year, things went a lot more smoothly. I think last year everything was rushed because it was started like as a split second thing essentially. But this year we had a lot more time to do stuff. Like we got a ton of funding links, for example, that was passed on to all the mentors. We had a lot more time to find mentors, mentees. We just had a lot more time this year, which was better for everything. So yeah, I guess that's about it. Any questions about the data or anything?
No questions. I guess not.
Doesn't.
Oh, yeah. Did someone have a question? Okay, apparently not. Okay, so one moment. I'll just pull the list of talks. Oop, here we go. Okay, so just in case, do we have anyone from group or project A1 that's supposed to present? Apparently not. So, in the interest of keeping the one group that needs to present early, so I think I'll call first to speak project I2. So Manjari and Suho, if you want to start presenting, you are most welcome. So project I2 is the second project in the interpretability track for evaluating interpretive methods for scientific reasoning. Manjari, are you here?
Yes, I'm here. Suho will present from the team.
Okay, excellent.
Okay,
I can see
yeah,
your slides,
do
so go
you
ahead.
see this? Yeah, and you all hear me well, right?
I can hear
Okay,
you as well.
so sure, yeah, great, thank you. I'll do quickly. Yeah, hello, I'm Suho. I'm presenting for like Team I2, led by Dr. Manjari Narayan, and then our team has me, Tommy, Hao Miao, Timothy, and Nubada. And our team's question is whether the scientific causal reasoning can be used to test the like various interpretability tools. And then here's the domain we're working on. It's a drugs. The cardiac risk is decided through a chain of like different proxies, and the compound blocks there's different ion channels that changes like the ECG that used to predict the rare fatal arrhythmia called torsis. The structure that matters on this diagram is the compound hit one channel. It doesn't it is that like compound doesn't hit one channel. It hits actually all of them at once, like potassium, calcium, waste sodium. So like there's like multiple different mechanism like how these compounds induce the risk. But traditionally, like the people only have focused on like this the potassium channel hERG. But like kind of this new test bed, they actually have all this information about multi-channel, and then this channel is like working not independently. That is very important thing. So like there's a very rich complex test bed to test the like interpretability tool on it. And yeah, it's just such something like we can hold calcium fixed, and very potassium is kind of hard to do that. And then there is like this dashed arrow here, the as well, and then there's a direct path, the everything the assays doesn't capture. There's some off-target effects, some trafficking, or like other metabolites. Like there's some other like physiological like conditions can kick in here. So what we want to do is ask is like, do LLMs use this like causal model, like or like kind of the partially correct heuristics, and like kind of there are a lot of like kind of the ways that LLM can shortcut this like kind of correct scientific reasoning and then give us a the risk assessment. So, and this is where we are. So what is done is the behavioral task that changes ground truth intermediate mechanism and context provided. So like we do have very firm ground of how LLM behave on like this testbed data. And then so we are in progress of like kind of unify and publish this data set. And then next, like we gonna focus on the mediation research, like how like different white box and black box mediation methods, especially inspired by modern causal interference, like from biostatistics or like econometrics. Uh, and so here's what the actual like kind of one example how what a like failure actually looks like, especially this like kind of the compound called the verapamil. It has a the very like high like hERG value, like hERG is a like they're the hallmark of hERG blockers, but its risk is low because it blocks calcium just as hard. So like kind of two effects cancel out. But the model gets the like kind of first parts right, like kind of it says it's blocker, it's okay. But now if we read this trace, it states like kind of that the risk is also depends on the drug's effect on the either ion channels in name sodium and calcium by name. It has the correct causal model in writing. And it doesn't use it, like kind of it falls back into this scaffold is structurally similar to non-potent hERG blockers and overcurs the list. So this type of like a failure mode is actually what we care about and what we often observe from the LLM model. Like kind of it's not missing knowledge, but rather than missing knowledge, it is more like kind of it doesn't reach the answer because it doesn't use like correct like a mediation process. So yeah, and this is a one the preliminary study that the behavior study that we did, and then we asked model that these two endpoints. There is like and one endpoint called like a QTC, and the other is like TDP. The QTC is what you observed from the cardiac ECG, and the TDP is the actual like photo the risk. But like when we ask like QTC and TDP both to the LLM to assess the like risk of like a certain compound, they always say the risk is the same for QTC and TDP. But when we ask like only one endpoint to the LLM, whether this compound is high or low risk of like QTC or TDP, they actually answer very differently. So, and when we compare like kind of the case that both asked versus like kind of one endpoint asked, there is a like huge mismatch between the risk labeling between the one endpoint versus the second one asked in the both asked cases, which means like kind of the model actually make a decision on the first endpoint ask and then kind of like repeat that one for the second endpoint be asked like in the same prompt, even though these two endpoints shows a very different characteristics. So yeah, so our next step is like kind of we can detect the effects. So now we need to attribute it. So like these three pieces. One is like attribution to intermediate mechanism, which is genuinely very hard and that points toward stochastic and separable effects from causal inference. And second is like mapping those intermediate regions onto internal representation and then next any realistic manipulation or mediating distributions such as interventions that stay where the model actually lives rather than pushing it somewhere it never goes. So yeah, we are happy to like work on like this project, and then I hope we can talk much more interesting results afterwards. Thank you so much.
Okay, nice talk, thanks. Um, is there any question in the audience, maybe? not much. So maybe I'll start with one. So you're looking specifically at so more medical applications right now. Do you have maybe other potential benchmarks or application for this, or is this just a benchmark for how well LLMs do at this?
Yes. So like the reason why we choose this specific like a medical application, it's not actually application, but this like kind of data set as a test bed is actually it has a very well defined the correct ground truth like reasoning process in it. Like kind of then we compare how LLM reason to this like kind of defined like kind of the reasoning process to reach to the how like kind of how to reach to the endpoints. So any type of like a data set that has a similar structure, we can use it. But this one is definitely like LLM is a lot of used a lot in the like a medical field drug discovery. So this is definitely like in terms of that one very important thing. But also I do think like kind of any like data set that has a this type of similar reasoning structure, and we can apply the like kind of similar methods to test the interpretability methods.
Cool.
Yeah, just to jump in there, I think we have a bigger hypothesis that like complex scientific tasks could make for interesting model organisms that don't exist right now. But yeah, I think that's we're working our way towards that.
Yeah.
Okay. Yeah, very interesting. Best of luck with that. Still no questions? I guess not. So we can thank the speaker. And so I think I will now call project A2, scaling information retrieval for domain embedding models. So thanks Suho and thanks Manjari.
Okay. How's it going, all?
Pretty good.
Good to hear. 1 second, please. Oops. Okay, so I am spearheading, my name is Enrico Cipolle. I'm spearheading the project for scaling domain embedding models. And we're going to briefly talk. Unfortunately, the fellow who was supposed to be presenting this to me today had an emergency and he couldn't make it. So I am going to be filling in. I think we should start coming off the bat a little bit strong. We actually had a call with the White House about our project. They are looking to implement our systems into their search engines. So we had a discussion with the Office of White House Counsel, thanks to one of our SOAR fellows, Andrew Hu. He had done an introduction to Ugana Eze, who works underneath Paul Adkins of the SEC. Previously, from before SOAR, we had done a large amount of SEC Edgar data processing. And as part of this project, we started training and building state-of-the-art financial embedding models for 10Ks, 10Qs, 8Ks, and all those different documents. We actually did provide a demo of the search engine directly to them, so that was very cool to see. And we're actually going to be expanding that and having a follow-up with the Office of the White House Counsel, hopefully very soon in the near future. And we'll see if we can actually get these directly integrated into Edgar to improve the semantic search of their embedding systems. Because right now it's quite slow, very keyword based, and as you can imagine, the search results aren't the best. So hopefully we're going to be working directly with them to greatly expand that. And it was very cool being able to meet with them in the Office of the White House Counsel. Next, because I am a big believer in building production grade systems, and as part of this project, one of the things that we had put together is we're building 3 or 4 different libraries as part of our project. We've currently already open sourced 3 of those 4 libraries. The pre-training library is still under construction, but what we had done initially is we had put together a large-scale distributed like embedding model and fine-tuning system that is built currently for HPCs and slurms. It allows you to scale hundreds of hyperparameter sweeps across a large amount of GPUs in a cluster array. And for this part of the project where we are building these domain-specific embedding models, I did want to focus largely on building something that is evaluation first. We found that many of the evaluations that are publicly available aren't very representative of the type of data that you would want when training these embedding models in production grade systems. For example, some of the stuff in MTEB is very hyper-specific for academic work, or it's very atom distribution. When you want a very strong embedding model, you want something generalizable, but at the same time, for specific domains such as US case law, it is important to have data that's representative of it. And if you go through RTEB, MTEB, MTEB v2, a lot of these systems actually, or I'd say these evaluations, don't have anything that represents what actual lawyers are going to be searching for. So we had worked with the Free Law Project. We worked with the Harvard Case Law Access Project on this part. We're also working with some very prominent lawyers such as Damien Rell, who had open sourced basically every melody in existence. He did a really cool project there. And we're taking these benchmarks that we are building, and then we're going to be adding them to a new version, hopefully, of MTEB or RTEB when that releases. We've already talked to the Hugging Face team and Nicholas Muninghoff. And then we released some of the encoders that we have already trained, which are state of the art. So when we went through and we had evaluated numerous of these with like an NDCG of 10, the best score that they were getting on these more niche domain embedding models was only about like a 0.71 or 0.7. We had gone through, taken basically every single piece of legal data in existence that we had collected. All this is open source, and we are going to be releasing that in a cumulative release along with many of the models. And we had found that we're actually getting extremely high rankings on a lot of this, even after doing multiple forms of decontamination, such as Minhas LSH, embedding near deduplication, and n-gram deduplication. So we wanted to make sure that there was no possible like overlap or contamination into the actual set, and we're still getting very, very high ranking on this type of data set. So it's really great to be able to see the very strong performance there. And now that we have proved out some of the results for these legal encoders, we're scaling this into mathematics with data sets such as the Ultra Data Map. We're expanding it into the SEC data, as previously mentioned on the first slide. Then we're going to be expanding it into PubMed and a few of the medical data sets that are open source as well. Another library that we actually built is that currently there are papers such as the NV Retriever paper, which do this type of hard negatives mining for building really efficient multiple negatives ranking loss or contrastive loss pre-training or fine-tuning data sets. We found that a lot of these, such as the ones in the Centage Transformers library, aren't really built for these distributed HPC systems. They typically run just on a single node. So what we had done is we had put together a library literally called Hard Negatives that you can install from PyPy right now. And it allows you to do this multi-GPU distributed mining across thousands of GPUs if you want to build a bunch of these indexes and follow like the best practices for NV Retriever. That's all now built into the library that we have released. On top of that, we're now doing exploration into different mining techniques, such as Minhash and BM25. We just don't want it to be the standard embedding hard negatives mining. We now want to do this and compare it against a few different results. The other thing is when you have something like Minhash LSH, it might be too hard of a negative, and BM25 might be too sparse of a mine negative. So it's going to be a very interesting ablation there as we're running that to see which type of hard mining ends up producing the best pairs for the multiple negatives or ranking loss training. Another thing that we have been working on is a large-scale data processing engine. Currently, with Lucas Soldny leaving LNAI and going to Microsoft, we've now lost Doma, unfortunately. So we're going to be taking that off his hands right now and started building an integration engine with Daft and Ray for these large-scale distributed data processing systems. Daft is, I've been working very closely with the Daft team, and what we have as part of this fellowship to integrate their data engine into a lot of tech, using like the best techniques in literature for processing large-scale pre-training data sets. We're going to be open sourcing all that, have already added some of the components that are built with the Rust engine, and we're working towards a full MAI Thinking One reproduction. I actually have an additional thread in that in the Luther AI Discord where we're discussing each of those components that are being implemented in open source, and we're trying to make this as efficient as possible. As part of this as well, we're actually serving a full weight Kimi K3 SGLang deployment because we want to do a large amount of creation of synthetic generations for data, as well as rephrasing, converting, and doing better extraction. One of the fellows right now has been going through some of the mathematics data set. And if you look at something like Ultra Data Map, right, it has a lot of text documents that do have really great mathematical information in them, but they are surrounded by really poorly developed text that's been extracted from forums, includes timestamps, dates, usernames, a lot of things that you really wouldn't want for that to be into a high quality data set. So we're building a distributed serving engine with Kimi K3, and then we're going to be doing the synthetic generation and extraction of a large amount of text documents to get the highest quality data. And then we plan on releasing those as part of this as well. That GitHub has also been released. It hasn't been built into a PyPy package yet because I haven't chosen a name for it. When that is done, I will be uploading that as well so everybody can install and easily use. The last part that I would like to talk about as part of this presentation is that we're doing a large-scale BERT pre-training. We're currently targeting around 6 trillion high-quality tokens, the largest ever BERT training, from my understanding, for pre-training an encoder model. I believe modern BERT was only around 1.7 trillion, and EDIN was around 2.1 trillion. We're now going to be scaling that up to around 6 trillion high-quality tokens, built with the data engine that I had previously mentioned, and we're composing a brand new pre-training code base for doing this new BERT model. And currently it supports both Ampere, Hopper, and Blackwell systems through the Quack kernels, through flash attention, variable length, flash attention 2, 3, and 4. We have been testing on scaling this to hundreds of thousands of H200s and have seen really great results. We're getting almost on 40% MFU on the larger models. With some of the smaller models, it's actually really hard to get any decent form of MFU because the data itself is taking up almost the entire computation and not the actual model weight. So when you're looking at like a 17 million parameter model versus a 1 billion parameter model, the 17 million is just almost the data engine loading everything throughout the entire portion of training. We're exploring a few different new research directions for encoders as well. Currently, from doing a lot of literature review, we really haven't seen anything using muon, nor muon, zclip. There are a couple embedding models. I believe the new Voyage embedding models themselves are using MOE, but Sonic MOE was getting really great flop utilization from a lot of our testing. So we're looking to include that with HSDP from the new FSDP2 library. We've also been exploring a few different versions of linear attention variants. There aren't currently a lot of bidirectional ones, so we've been looking at implementing some of those ourselves. And then we do support the variable length flash attention training, as well as the data processing to be able to create everything with a cumulative seq lengths, max indices, and what is required to scale that out in a distributed setting across a bunch of CPU nodes. One very interesting thing, too, is we've been looking at using the Super BPE tokenizer. A friend of mine, Stefan Tokens, has done a lot of work on tokenization. And we are having all the fellows right now doing ablation studies when you take a cased versus uncased, 3D versus BPE tokenizers, and try training a bunch of those for both post-training and pre-training of models. The GitHub for this has not been released yet, but there are multiple members from Luther AI who are actually working on this project, as well as the SOAR fellows and a few of the modern BERT authors themselves. So that's just really a run through of everything that we've kind of been doing so far since this project started.
Okay, quite ambitious.
Oh, you got to be, right? That's the Pygmalion effect, right? You set the standards very high, and then you work to meet them.
Yeah. So correct me if I'm wrong. So you start with mentioning this White House thing. So is this maybe the fastest? Like that's probably the fastest application for a project I've heard, because you've not even finished.
Yes. This is interesting, is that we have done a lot of work with the data processing for the SEC Edgar data prior to this project. So it's not like that just started right off the bat and then we had an introduction to the White House right away. There was quite a bit of work that was done on that. But then we had started training these models and putting the search engine and everything else together, in which one of the SOAR fellows, Andrew, is friends with one of the White House office counsel, Ugana Eze. He was able to get us an introduction to them. We had demoed him the search engine, the models, a few things like that. And then we're actually looking to hopefully have a follow-up very soon where we're able to present even more information, research, and promote open source to the White House directly, right? Like that's a really big portion of this, is that having their backing and being able to promote open source AI is something that currently isn't being done with a lot of what you see in the news today, but I hopefully we're going to be able to branch in there and do that.
Yeah, very cool. Is there any question from the audience?
I have a quick question. So you mentioned about the training of on multiple GPUs using like sweeps of multiple hyperparameters. What are the existing solutions that are in the industry right now, either like open source or closed source, that people use for this, apart from like VLLM and SGLang?
There's Optuna. There is HyperOpt. There's a few different niche libraries. RayTune actually is another one. I think there's like 3 or 4 hyperparameter tuning libraries that exist. They don't currently scale too well for being able to do that, especially for Slurm or HPC-based systems, because Ray integration is really built for its like heterogeneous architecture, right? But when we wanted to do this, we wanted to be able to queue hundreds of jobs in parallel, especially when you're using Slurm-based systems. There's always like wall times and queue times for being able to do that, which makes it really difficult to use something like Ray or one of the existing libraries that is currently available. So we figured that we'd put something together that could use Slurm arrays, have one job running on each Slurm array, and then be able to re-queue when that wall time has run out, which is something that's typically not available in a lot of libraries, or maybe something that I am particularly not aware of myself, but does exist. And if it does, I'd be happy to try it out.
Nice. Any other question?
I have a question. This is kind of a silly one, but how many GPUs are you training on? Do you own all of them?
We have a very substantial amount, yes, through
Wow.
our organization.
I see. Yeah, because when I applied to get funding and GPUs, it was very difficult for them. So
I would say it's extremely difficult to get access to compute, and it's probably getting worse every day. I'm not trying to be a Debbie Downer, but every GPU location or hard drive location that I've had conversations with, whether it's like Crusoe or some of these other organizations, but I have a lot of friends at Crusoe. They previously had sponsored some projects, but they had moved elsewhere now. And the thing is that the GPU capacity is essentially zero, because it's either a startup or large organization, and I think getting that sponsored is probably going to be very, very hard to do.
Okay. If there are no other questions, I think we can move to the next project. So I'm calling project I3, effective rank and semantic compression on foundation models.
That's me. Hi guys, I'm Angus. I'll have to apologize here. I don't have any slick presentations like everyone else. So yeah, so basically the core focus of our present study is what's called the Platonic representation hypothesis, and also the Aristotelian representation hypothesis to a lesser extent. So which basically the idea, if you're not aware, is that different models should converge to a shared manifold representation of some underlying reality, right? Especially as the models get stronger and get more data right? So we've been studying this in the context of astronomical data, partially because you know, the astronomical data corresponds like pretty sort of clean physical properties, you know, redshift, magnitude, stuff like that. And also there's a lot of astronomical data. There's plenty to work with, and existing vision foundation models haven't been like extensively trained. So what we've been focusing on specifically are essentially two related hypotheses. The first is that given a model, typically a vision model like VIT or Dino V3, given the activations of those models with respect to an astronomical data set, there should be a low-dimensional manifold on which those activations live. And that given a point on that manifold, there's a local basis centered at that point such that the basis vectors are broadly interpretable. The second hypothesis is that there is non-trivial curvature on this manifold, and that this curvature should kind of give us essentially a, how shall I say, an index of how interpretable the local basis is. So for example, you know, like linear probes, we should expect that in regions of high curvature, our linear probes aren't as good as they are in like low curvature regions, because, you know, any like orthogonal basis we place there is not going to be very faithful to the actual underlying representation. So the first step has been figuring out the effective dimension of our activation methods. So primarily for that, we started looking at both PCA and graphical methods such as ISOMAP. PCA performed pretty badly, both global PCA and local PCA. So local PCA is just like regular PCA, except you don't center it. You just take it with respect to a, you know, some like local hypersphere. They really sucked for dimensional estimation. They massively overestimated by a factor of about 9 to 10. The reason being that like PCA in general is very good when your underlying data distribution is like mostly Gaussian and isotropic, and when you know, like the noise spectrum is reasonably well behaved and low magnitude. And so we did, you know, a couple of tests on like different types of synthetic manifolds, and in most cases PCA just sucked. It was really bad, which is retrospectively not that surprising, but I was kind of disappointed because, you know, like one really sort of nice theorem from the literature is that PCA subspaces provide was essentially like a reasonably faithful, I guess you could say, estimator of the local tangent space of a given manifold. So what we found is that graphical methods, especially ISOMAP, were much more robust in the presence of you know, nonlinear data distributions and more noise, and generally, like, you know, across the board yielded like better estimates of like effective dimension across a wide range of cases, with the one caveat that especially in ISOMAP's case, like the actual embeddings produced by ISOMAP were not great. They were not good at all. So what we ended up doing, what's kind of been like the best thing so far, has been using sparse autoencoders with what I call a learnable shared basis. So if you take, like, so because, you know, the main thing we kind of care about, I should have mentioned, it's very early here in Australia, so you have to bear with me a bit, is that in evaluating the Platonic representation hypothesis and Aristotelian representation hypothesis, our main sort of like tool of the trade for evaluating if two different representations are similar is evaluating what's called MK, mutual K nearest neighbors, which basically is a measure of, like, you know, given the geometry in one space and the geometry in another, how similar are they? right? So isomap embeddings, when we compare isomap embeddings in two different activation spaces of the same data set, not great. Much worse than simply taking like the naive Euclidean embedding. Whereas if we take an SAE, that's a lot better. But because different dictionaries for different SAEs and different activation spaces aren't there's not like a direct apples to apples comparison there. We have to we found that learning a fine basis mapping between those two spaces yielded an SAE that was much better in terms of MKNA, sometimes substantially better. Whereas compared to random control, because you also have to be careful of the possibility that the affine basis is sort of cheating a bit compared to just like taking random hyperspheres in both cases, we get almost zero MKNA. So we're pretty sure that the SAE method does yield like a pretty good low dimensional manifold, though interpretability is still an issue. Another interesting technique that I started exploring pretty much last night is also block sparse filtering. So if you guys see the Goodfire paper from it was about a month or two ago, the basic idea is that you take an activation and you decompose it into essentially not a set of sparse codes, but rather a set of subspaces of those sparse codes. So the idea is you have a set of very low dimension underlying manifolds, which is sort of orthogonal to each other, right? And we kind of treat them as a basis, and that seems to be yielding even better MKNN. But have to do a bit more testing to be certain of this. The other thing we've been testing for is curvature, right? Because the idea is ideally for a clean test, especially with the Aristotelian representation hypothesis, we also want to know which regions do have a clean basis, a nice relatively linear basis that we can easily interpret, and which are a bit too chaotic. So the idea is that given a non-trivial manifold, right, it'll exhibit curvature either extrinsic or intrinsic. Although, in our case, the difference between the two is a bit troublesome, or really it just doesn't really exist in the way it does in classical differential geometry. But the idea is that given our data set, we have a bunch of auxiliary physics information associated to each data point in that, in our case, images of galaxies in that data set. And the idea is that the theory is that high curvature regions should exhibit worse performance from linear physics probes, right? So this is where we've been a little bit more stuck, because going through the literature, most methods of curvature estimation are just no good. They do not seem to really yield consistent results. There is a general problem here where in this particular field of study, you do want to be able to bring classical differential geometry methods to bear, because it feels very natural. You want to find a nice metric, you want to do all that stuff, and it just doesn't really work that well. It does not, because you're dealing with a very, very high dimensional space where the underlying support is essentially discrete, even though it's technically continuous. In practice, it's discrete. And, we've been kind of experimenting with using variational autoencoders to sort of infer a continuous support. But the problem is the best methods in that kind of area require prior knowledge of the manifold's topology, and that's also not trivial. So what we've found so far is that the best estimator of curvature is local PCA, which acceptable for effective dimension. Essentially we just take, a given neighborhood around the point and, essentially do bootstrapping with the PCA subspace. So we just, bootstrap a bunch of points, compute the PCA basis, and then see how that varies over the samples. Low curvature regions should exhibit like fairly low variance, high curvature regions should exhibit very high variance. And what we found in that regard is that once we tested out physics probes, there was definitely like a positive result. So, low curvature regions consistently exhibited, fairly high physics probe performance and consistently at the top of the range, and also very low variance in terms of overall performance. Like they were all clustered very much around, a certain level of accuracy. Whereas in high curvature regions, it was a bit more like not so much low accuracy. It was, definitely like a non-negligible correlation, but it was more in the sense of like we see a lot more like very poorly performing linear probes, but also like some okay performing linear probes. So primarily it's not so much like a clean negative relationship, it's a question of like high variance, is it low variance in accuracy at low curvature versus high variance at high curvature. And so the big question is like, can we come up with like a better measure of curvature, since PCA kind of failed so far? It seems like, I guess to some extent that's not really that surprising, because like the whole point of PCA is you're picking up like linear variance directions. So curvature really is measuring like the failure of a space to be like linear to some extent. So yeah, we'll see about that. So where are we going from here? Well, now that we have like a reasonably decent sort of low rank representation and like an acceptable measure of curvature, even though the two methods are sort of like very distinct, the big question from my end, from my mind, is like, how do we interpret this? And this is where I think block sparse featurizers are probably a bit the best tool we have, because it seems like with SAE codes, there's looking at like transference between different representations, there is like a definite like low rank bipartite matching between the codes in two spaces, but that bipartite matching doesn't really seem to form like nice distinct clusters. Everything's very diffuse. Whereas my hope is that we can think of like the BSFs, the block sparse featurizers, as essentially like subspaces where certain, I guess you could say, clusters of relevant features in the activation space just basically get like blanked out. So there might be like a subspace which is like only spiral galaxies live, and another subspace where only smooth galaxies live, and we can use this like tool to sort of like decompose an activation into almost like a state vector. So we can see, this has got like a certain amount of activation in this space, and we can sort of like think of this as like a probability that it exhibits a certain property. For numerical properties, it's a bit trickier, I think, but we'll see. So yeah, that's the essence of it. Yeah, so our presentation's been a bit messy and very busy lately, but does anyone have any questions or comments?
Well, thanks for the explanation, at least. If no one else has a question right now, I do actually have one. Yeah, maybe I'll start. You mentioned a bunch of graph manifold estimation methods. Have you tried something like diffusion maps or like spectral methods in general? Because at least I'm like more of a mathematician, so I'm I assume much more nicer conditions than in practice. But I know there are a bunch of theorems like, so there's this paper, consistency of spectral clustering, for example, which tells you that if you use diffusion maps or spectral clustering, which is essentially the same thing, you do correctly estimate clusters, for example.
Yeah, that's a great question. And it does actually, yeah, point to a bit of a blind spot. So diffusion maps are something I sort of looked at early on, or thought about early on, and just sort of like didn't really get round to because SAE seemed to be pretty good at the cost of like not being entirely satisfactory. So that thank you for reminding me. Actually, that is a good one to look into before we kind of move forward. As for spectral methods, well, I mean that's a pretty broad field. I mean, look, any representation I get, I try and like find its eigenvalues, if that's what you mean. So, for instance, with the shared basis matrix, the first thing I kind of looked at was, okay, can we kind of extract some meaningful information, um, from the eigenvalues of this thing that kind of like give us, an idea about like what the feature space might be. And it's something I think I will have to kind of like revisit once we sort of like get more deep into the interpretability side of things. But yeah, that's primarily, I guess, our focus has been on like PCA, which I guess is a sense of it's a kind of a spectral method, as well as graphical methods, and in part because like the data sets are so huge and compute is so scarce. Like I've been doing most of my work on my own graphics card. So the other big focus has been like making it, like focusing on methods that are like relatively computationally tractable. Um, so yeah, but that is a good point about the diffusion maps. I would kind of like completely forget about those. So I hope that answers your question.
Yeah, pretty nice. Sadly, I don't have any idea about curvature estimation. That does seem like a much more difficult problem. So good luck with that.
Yeah, there's the literature is very sparse, and it is one of those issues where like classical differential geometry has a lot to say about this, but when it comes to like dealing with massive high ultra high dimensional manifolds on fairly unlike I said what effectively discrete supports, like the classical methods become like very ill conditioned very quickly, and a bunch of the other pre-existing methods kind of like suppose a metric that we kind of come into assuming is not the correct metric. Like we don't think that like a Euclidean metric is really like the correct metric in this case, because we could tend to see like a lot of equidistance in like our raw activation space. So yeah, it's a challenging one.
Okay, thanks. So I see the clock is ticking. So is there any question from the audience? No. Okay, then let's thank the speaker again, and we can move on to project I4. So how do foundation models see the same sky? So you'll see that the next few projects are related in topic and in mostly the like mentor pool as well. So yeah, we'll be hearing about a lot of astronomy right now. So thanks again, Angus. So for I4, the name I have is Keeks. Are you here?
Yeah, I'm sorry. I was trying to start sharing screen.
Yeah.
1 second.
So normally you should be able to do that without like me enabling you. Yeah. Okay. I see your screen, and I think other people do as well. Yeah. So take it away.
Okay, Kiki, you're muted.
Thank you. All right. So what we're working on, very similar to what Angus described, we're trying to extend the Platonic universe paper. We're trying to take a slightly different approach, and the idea here is if we can take a number of techniques that more or less already exist, maybe we can get close enough to a position where we can say that we haven't necessarily disproven the PRH. So the idea here is we basically take a slice of the same galaxy, and what we'll get into later is that we've created this cross-match data set. And the idea is that if we take features from both of those, if we feed features from that data set into two different sets of models, and we basically look at the model layer by layer, then if the PRH holds, then at some specific layer, we'll be able to see where the I guess the threshold between what the instrument, the telescope has provided in terms of data, changes to potentially like revealing the underlying physics. So as listed here, we're using a number of models, including Dino V2, V3, IJEPA, Lava, and on the astronomy side, obviously using Astro PT as well as Amazon Chronos for the time scale, which very interestingly allowed us to kind of like flatten some of the features that we're capturing in the data set to one dimension. Number of different methods here, right? MRR, MK nearest neighbors, also using the Prokofsky distance in order to try and figure out that absolute distance between two manifolds, a decoupled CKA, and a number of other features. What we've done so far, as I mentioned earlier, we compiled that data set, and now what we're actively working on is basically just running 4 experiments. Let me get a list of the experiments. Basically, one, trying to pass the data through those foundational models layer by layer. Second one being using the Procrustes distance to see if we can calculate that absolute distance. The third one being to try and figure out at what layer shows the best or the most amenable physics, if that makes sense. And the fourth experiment basically being, can we denoise the effect that the telescopes or the instruments themselves have on the data set so that way we can better decouple to what extent are the models coming up with the correct underlying physics, or to what extent are the instruments more or less guiding the models to what we would view as the correct answer. Yep. And this slide basically we're just describing more what I was saying earlier, in the sense that we're passing the data through the models, looking layer by layer to assess where the threshold between what the instruments are doing, or not the instruments, but what the data provided by the instruments kind of nudges the model into perceiving is the correct answer versus the underlying physics. But yeah, plenty of work for us to do, and we're, I think, going through it quite well. Any questions? Sorry, that I know that was a lot shorter than the previous one, but yeah.
Yeah, it's fine. I mean, given that it's been an hour already, I appreciate the swift presentation. So thanks a lot. Okay, are there any questions from the audience? Okay, again, not. So can you maybe clarify exactly? So, are you using these foundation vision models to see, like, probe what they know about astronomical data, or like I'm not exactly sure what you're doing here.
Right. So the idea here is, let's say we take a celestial object or a slice of like a subset of celestial objects. We feed them through we feed them through models that can obviously see versus models that are more trained on astronomy. And from there, we see where within the embeddings, or sorry, we look at the activations within the embeddings, but Shated, please correct me if I'm wrong here.
One thing that I can step in, one thing that may not be immediately obvious is that the way you test whether a model has learned physics is by doing linear probing from its embeddings to a bunch of physics labels that come for free with all of these astronomical data sets. So why astronomy specifically is because not only do you have a bunch of modalities or data in modalities that pre-trained foundation models can have or can load, but you also have a bunch of labels that, so for example, galaxies have things like specific star formation rate, metallicity, which ordinarily need to be fit with a lot of like specialized tools, but you can try and bypass that with deep learning and just try and figure out whether linear probing on a certain layer has a high correlation with the physics labels that are provided with the dataset. And the idea is you investigate this across many modalities, many models, and see where the alignment peaks. There is some literature suggesting that it should peak somewhere in the middle, but we're also doing some stuff with designing careful methods to remove the effect of the instrument itself. Does that answer your question, or?
Yeah, it does. Thanks. So yeah, interesting stuff. It does look difficult. So best of luck.
Thank you.
Okay. If there is no other question from the audience, I think we can move on. So to project I5, interpretable conformal prediction for cross-survey astronomy. I think Meho, you're ready to go, maybe?
Yeah, just a second. I'm sharing the screen.
No problem. And also, so thanks again for the previous speaker, by the way.
Is it visible?
I can see your slides, yes.
Okay. So our work is also quite related to what OPT explained. But we are also working with the various foundation models and their embeddings and cross-match survey astronomical data sets. But we are taking a bit deep route into the uncertainty quantification and flagging out astronomical objects which behave strangely in comparison to others. So what our project is all about is that modern astronomical surveys observe the same sky with different depths, resolutions, and wavelengths. So, for example, here we have three different kinds of astronomical objects, three different kinds of galaxies, and we have three different kinds of images for all of these three obtained from three different astronomical surveys. So, although they belong to the same modality, you can see that there is quite a bit of difference among them. And now, when we train foundation models on these data sets, what we expect that is the embeddings for the same object across the various surveys should stay aligned. So, in this project, we are trying to develop an interpretable conformal prediction framework, which would help us in answering some questions like, are foundation model embeddings of the same object reliably aligned across surveys? Which objects are hard to align? Are there some rare morphologies, some weird shapes, artifacts, or blends of faint sources which are hard to align? Which foundation models can we trust for cross-survey transfer? And do they all fail on the same objects or different ones?
Is a basket of models more reliable than any single one? Can we combine embeddings from various foundation model and come up with a better representation? Two hard objects, the objects which are difficult to align across surveys, share something that is not in any of the catalogs. So our methodology starts with training a translator model, which is basically a regression model, which translates the embedding from a source survey for a given foundation model. So, for example, our source survey is High Suprema CAM, and we are translating it to a target survey, James Webb. And once you obtain these trained translator models, uh, we will create three splits on our dataset: train, test, and calibration. And on those held out calibration objects, which are there in calibration split, through them we will calculate calibration residuals. Now these residuals will be are used for calculating the conformal quantile, which is nothing but percentile of the residuals obtained on those held out calibration objects. So I'll be explaining how the percentiles will help us. So this will give us a coverage threshold. So like 80% of the, so if the coverage threshold is like 90, we are saying that 90% of the time, our 90% of the time our model is correct in translating the embeddings. So through this, we will have an uncertainty quantification. We will have a small certain region of uncertainty, a small radius, a conformal radius, which will tell us which will quantify the uncertainty uh, in cross survey translation. So if the radius is small, so this conformal radius is nothing but the chosen percentile of the calibration residuals. So if this, so let's say if you are taking 90 percentile, 90% coverage threshold. So if this coverage is small, if this radius is small, that means that our embeddings are better aligned and we have high reliability. Through this uncertainty quantification, we will further do two kinds of analysis. First of all, we would like to flag the objects which fail to align across surveys. So they might hold some interesting scientific properties, like some special types or some special shapes. So we would like to learn what are those. And at the same time, parallelly, we would also like to analyze which backbones representation align best, and why some models have better alignment than others. So as of now, we have some preliminary results. So we have trained translator models for three cross-survey astronomical data sets, and we have done that on different foundation model embeddings, starting from AstroPT. So first three are for AstroPT. So this is a domain-specific foundation model, astronomical foundation model, pre-trained on astronomical data. And the other models are general purpose foundation models like IJEPA, ConvexNet, Dino, VID. So, and we have done the same conform analysis on it, and we have done it for different coverage, starting from 80, then 90, 95. So as we keep on increasing our coverage, we are asking for more reliable results from our model, for a more reliable alignment from our models. And a very general pattern which we see here is that as we increase the coverage, as we increase the confidence in a model's translation, the conformal radius also increases. So conformal radius, as let me remind you, is nothing but the 90th percentile of the residual, which means that if we ask for more reliable results, we have to trade it with precision. So this graph basically shows that our calibration framework is working fine. It is showing reliability precision trade-off. Then another observation which is worth noting here is that AstroPT gives quite smaller conformal radius than all other foundation models, which might be due to because AstroPT is pre-trained on astronomical data, and the representations learned by AstroPT are easier to align across surveys, while all these other models are trained on general purpose image datasets. So in our covering experiments. So as of now, we have flagged the objects which fail to come under the region of certainty. So we would like to analyze them. And at the same time, we would also like to see if the different kinds of explore different kinds of methods so that we can combine embeddings from different foundation models and generate basket embeddings and see if they can perform better uh, at downstream task or not. Yeah. So that's all. Thank you so much.
Okay, quite interesting. Is there a question from the audience? Okay, apparently not. So maybe one question. So these AstroPT models are trained specifically on astronomical data, but they do not necessarily have any kind of like constraint. Like I'm thinking of something like geometric deep learning, where like this you're essentially trying to enforce some kind of invariance under, I guess, sampling or survey conditions. So like you basically want to build in, or you would like to have some kind of invariance property, but I guess it's not enforced here in any of these models, right?
Yeah, we are working on normalized embeddings. So uh, since they are normalized, so this rules out the invariance among them. I think the difference in astropic performance is due to the kind of representation which are innately different from other models. I hope that answers your question.
Yeah, thanks. Okay, so in the interest of time, if still no one else has a question, I think we can move on to the next speaker. So thanks again, Mehul. So project I6, the structure survive scale, diagnosing hierarchy in SAEs. So I think I'm waiting for Martin.
Yep. Let me just share the screen.
All right, take it away.
Yep. Okay. Yeah, so I'll be describing our project, the structure survive scale. It's another interpretability project, namely about sparse autoencoders. And it's a project with 2 mentors, Elena and Gonzalo, and 5 mentees that you see in the upper right corner. And as you usually do want, what you usually do want to do with sparse autoencoders is to extract some kind of meaningful concepts from neural network representations. But the meaningfulness that can be defined on different levels of abstractions or specificity. So you can ask yourself, do I need, for example, latent representation of an apple, or do I want to work more abstractly with latent representation of fruit? And this can be to a degree controlled by basically defining or by changing size of the sparse autoencoder, where bigger dictionary usually means that you will get more specific concepts. But this is not universal. It comes with issues. People have found issues like feature splitting, where general concept sometimes splits parts of the concept into different latent absorptions or unwanted composition. And you can arrive at some kind of Frankenstein latent representations. For example, one latent neuron which is representing, let's say, all fruit except for apple, but also fruit that is round, so kind of combining together shape with the concept of fruit. And there have been architectures like Matryoshka SAEs, temporal SAEs, or different kind of Matryoshka SAEs from the paper called Priors in Time, and they all claim to recover hierarchical dictionaries. They are doing so by explicitly reserving parts of their latent space to different hierarchical levels. Now, the problem that has been identified by our mentors already is that these papers don't measure coherence of the parent-child structure. What I mean by that can be seen on an example of some kind of more real-world model, GEMMA2, 2 billion parameter GEMMA2, where, for example, Matryoshka SAE often creates some kind of degenerate hierarchies. For example, top-level features which have no children, lower features which have no parents, or super parents that are kind of arbitrary super parents which do not represent concrete concepts, but instead they track some kind of high frequency tokens like spaces, definite articles, and stuff like that. So the aim of this project is to critically audit different SAE architectures, those three architectures, and to study at which point of the at which point of complexity the hierarchy fails. So we're trying to train sparse autoencoder architectures on domains of increasing complexity, starting with very simple domains and going into real-world domains. And we are trying to evaluate on each of these domains the original. We are trying to evaluate the architectures with some metrics, and I will talk very shortly about that. So one of the teams within our group is working on metrics. So there have been some metrics that have been predefined already in the description of the project. These are the 5 black metrics. One example of that might be, does the child fire only when the parent files, and do the children together account for the parent? So you can look at the structure, at the relationship between a parent and child from different points of view, and you are trying to determine whether there is an actual relationship in terms of a real hierarchy. Now, I was talking a bit about the fact that we want to start with kind of very synthetic settings. So the team behind metrics has developed some very synthetic settings. Then we're continuing with some toy models from the mentioned papers. And we are hopefully we will be able to finish off with SAEs on real models like 2 billion parameter Gemma2. If you're interested in this, they have built even some very nice dashboard with results. I mean, you can either check it now, or I can also direct you later to the appropriate people. When I was talking a bit about the increasing complexity of the settings, one kind of interesting, let's say, compromise or mid-level complexity setting is this PCFG, probabilistic context grammars. So a member of our group is working on this. So you can imagine it as some kind of semi-formal language or formal language, but which has quite a lot of real-world usage. And you can maybe remember these kind of syntactic trees, from your school years. Yeah. Again, there are some very nice dashboards aggregated by April, but I will probably direct you to her if you're interested. And finally, there is a team which is me and Lucas. We are currently working on trying to ensure that the 3 SAE architectures are implemented well and that everything works together. And with that, that's basically it from me. If you have any questions.
Okay, thanks for the nice talk. I'm going to ask if there are any questions again, but yeah, as I expected. So maybe like what would be, so you have like sort of multiple sub projects within one project, right? Like, do you have any next steps right now, or like?
So we kind of need to, from my point of view, we need to finish multiple of these projects. Inherently, this project is kind of trying to prove some kind of, let's say, negative result, which would show that actually most of these architectures do not work, and we want to show where they fail. So we are trying to progressively train these SAEs on these different levels of complexity, and each one of them will probably work to a degree, like they will work on the toy models, but at some point they might fail. They might fail, for example, on the context-free grammars, or they might fail even earlier. And that's kind of an interesting, interesting scientific result to see, like whether there's actually a working way to extract some kind of structure from SAEs or not. I might have diverged a bit from the question, so sorry.
Yeah, no problem. And so, if I recall correctly, like this started from, like this project is a follow-up from one of last year's projects, right?
Yeah, but that was a follow-up of I think Elena and Gonzalo. So
Yeah.
none of the other, none of us mentees were present there. But yeah.
Yeah.
Yep.
But I vaguely recall the older project. So yeah, it's nice to see it being continued. So thanks again. Still no questions from the audience. Still no questions. So thanks, Martin. And so moving on to project I7, replicating seed stability results in sparse autoencoders. So yeah, from now on, it's mostly going to be SAEs. Okay, so I'm waiting for Tianai.
Yep.
Are you here? Yeah.
Yes, can you hear me fine?
I can hear you.
Okay, perfect. Sorry, I'm just going to share my screen. Okay. Okay, can you see my screen?
I can see your screen, and I think other people can too.
Okay, perfect. Alrighty, so yeah, hi, my name is Tiana, and so three of us, Mario, Jaden, and I, we are working on C stability in sparse autoencoders, and our mentor is also Gonçalo. So to start, I'm just going to give like a very basic, like, I guess, overview of SAE or sparse autoencoders for those that don't know. So essentially, so we start by giving, some text to a model, typically an LLM, and then we choose a specific layer of this model, and the text produces a dense activation vector. Here at that layer, which contains like a lot of overlapping signals that could be difficult to interpret directly. So the point of SAE is to essentially, like, it's a tool to interpret this like really hard to interpret overlapping signals. So the SAE encoder maps this activation into like a much larger set of features, so the sparse features, and only a small number of those features are active for any particular input. And that's what makes it sparse. And we want it to be sparse because that encourages the SAE to explain the model activations using, only a small set of features instead of like spreading the information across everything at once, which would make it a lot more, like the learned features, a lot more distinct and more useful to interpret, basically. So then the decoder, it then combines those active features to reconstruct the original model activation. So yeah, so basically during the training, the SAE, the latent feature, it's like encouraged to reconstruct the activation accurately while keeping the features sparse. So for interpretability, we basically inspect this layer to see like when each feature activates. So for example, if like this specific feature often activates with words like oak, pine, or maple, then we might interpret it as like a feature related to tree species. So yeah, so essentially we're looking for shared patterns and basically try to form some sort of like possible interpretation from it. Okay, and so moving on, imagine that we keep the model, the training data, the SAE architecture, training setup, everything exactly the same, but we only change the random initialization. So we only change the seeds, basically. And then we train this same SAE independently, so for two different seeds. And if the learned features are capturing stable structures in the model, we might ideally maybe expect many of them to be reproducible across the two runs if only the seed is different, because it's the same for everything else. But in reality, we find that's often not the case. Some features may appear in both seeds, some may not. So essentially, it's kind of hard to trust like the SAE's interpretations, if the learned features, they change across seeds. And I guess like a more general question really is not necessarily like, if every individual features is identical across run, but it's more of like what aspect of the learned representation remain consistent. Since we use the features to interpret models, we really do need to understand like how reproducible and stable those interpretations are. Yeah. Okay, so basically what we're doing as a group, we have like kind of like 3 different directions, but they're like all related and overlaps a little bit. So essentially to study this like C stability, first we're looking at architecture. This is what Jaden's working on. So we're looking at whether changing the SAE design can make the learned representations more stable across seeds. And then second, we're looking at metrics, which is what I'm looking at. And basically like how should we compare like to SAE seeds, and whether different ways of, like measuring the similarity across seeds would give us different answers or like different framing of like the stability. And third, we want to look beyond just like one-to-one feature matches, and because like even when individual features, even if they don't align closely, like the two seeds could still recover similar large-scale structures. Yeah, so now I'm just going to kind of explain a little bit more of like what each of us are working on. So on the architecture side, Jaden, he's kind of comparing C stability basically across several SAE designs, since like some of these architectures, they organize features in different ways. So he's looking at whether some design might produce representations that's more consistent across seeds versus like other designs. And for me, in this like metric direction, so I'm essentially comparing the same SAE setup across different seeds using different metrics, measuring similarity. So at the feature level, I looked at cosine similarity, which is like in the original paper that Gonçalo published, that our work is kind of based on, and also co-activation using Jacquard. And at the representation level, I looked at global CKA, and I'm also planning to look at other methods as well, like SBCCA. So the figure here, essentially, it shows like a distribution of like co-activation with Jacquard, the similarity scores after matching the features with like Hungarian matching. So it's the matching features between one pair of seeds. So you can see that there's a large population near 0. So that means like many match features, they don't activate on a very similar set of tokens, essentially. But there is kind of like a broad tail to like the moderate to high overlap kind of side. But I think like the current picture is that feature level wise of matching is pretty mixed and probably unstable. In contrast, when I was looking at global CKA, the score is actually really high for the C pair. So it's like around 0.9, it's like 94% maybe. So like these numbers, they're not exactly like comparing apples to apples, but like, so you can't exactly compare them directly. But I feel like kind of like the contrast, like you get really high score of similarity when you look at global structures, kind of, it's like, it's kind of encouraging and kind of points to like the second bullet point here that we want to, like look at whether two seeds can have very similar overall representations, even when the individual features do not match really closely. So yeah, and on top of that, I'm also going to like repeat like this analysis for more seeds and test whether pairs with like higher representation level similarity scores. So, like, for example, global CKA scores also tend to have higher fraction of individual overlapping features. Okay, and so this is what Mario is working on. So he's basically looking beyond the one-to-one feature matches. And in this figure, from what I understand, basically he took unmatched features, so like orphans, from many SAE seeds and compare every pair based on how often they activate on the same tokens. So each row and column is like one feature, and the brighter values means stronger co-activation. So essentially the takeaway is that even when individual features, they don't match closely across different seeds, they may still organize into like similar larger scale groups. So yeah, and then he's now looking into like to inspect, the individual features in these groups to see if they actually share like some sort of coherent interpretation. And yeah, that is it. That's what we're working on. Got a lot of stuff going on.
Pretty neat. So in this picture we have this like block structure. So I'm guessing does each block correspond to like a layer of the
So I think they are individual features. So each tiny ones is like an orphan feature from like, I think from a total of A seeds, like A runs.
Okay.
Yeah, that he took.
Okay, but so where does the block structure come from here then?
I believe it's from how he clustered, like he used like the latent clustering, I think, which I think kind of gave the structure. I don't know if Mario's here, but yeah, that's how I understood it.
Okay, I mean it definitely looks intriguing because I mean maybe it's like artificial, but it looks like quite a strong structure here. So interesting to see.
Yeah, we're still looking into it to see if that's like it's valid or not, but yeah.
Yeah, so maybe like a thought that popped into my mind when listening to you is like maybe you would have a model where you want to describe the probability that given that your SE learns a certain feature. So it's like, so basically like let's say each feature has a latent probability of being learned, and okay, maybe you cannot actually compute that, like, but like maybe you can do like some physics style ansatz, assume that the probability follows this, and maybe do something, but I don't know. I know nothing about this, so might be interesting.
Yeah. So like yeah, like are you talking about like the different metrics of measuring how similar they are, or
I guess I'm thinking more like theory, like okay, suppose a priori there is like a probability that your SE is going to find a given feature, and try and like maybe start with like a mathematical description which may be an approximation of that probability, and
I see. That's interesting. So from what I know, or I guess learned so far, is that SAE, like it's either it activated or not, like just with the co-activation, for example. But there is, I believe there's like a strength to it, like how strong was the activation, and I don't know, maybe there's like some sort of probability there that, yeah.
Yeah, I mean, interesting stuff anyway. So looking forward to see how it progresses. Are there any questions from the audience?
I have a brief, well, maybe comment. Just kind of following on from what was said before. One thing you might want to consider is building like an Ising model out of the co-activation. There was a paper on that. Kind of research that. Then you that basically is like building like a probability distribution.
I see.
Yeah, I think I remember that paper.
Yeah, it was a good one. And then maybe like test like the KL divergence between like Ising models generated from like two different seeds or something.
Okay, yeah, that's cool. Yeah, if you have a link to the paper, or I can just Google it actually. But yeah, that's good to know. Thanks.
Yeah, so very interesting comment, thanks. So I think we can move on to the next speaker. So thanks again.
Oh, sorry, I'm just gonna stop sharing. I think.
Yeah, no problem. So thanks, Kianai. So yeah, project I8, activation verbalizer causality experiments. So Abhinav, if you are still here.
Hi. Yeah.
Hi. I can see your slides and I can hear you.
Okay, great. Let me do that. Okay, so yeah, thanks for inviting us. So this is joint work with Kaylee and Daniel and supervised by Gonzalo. So our project is on natural language autoencoders. So let me just explain the idea behind this technique. This was developed by Anthropic recently. So you start with a text and you take a token and you get the activation of that token from some layer, typically a middle layer. And the natural language autoencoder has two modules, the activation verbalizer, which is kind of like an encoder, and an activation reconstructor, which is kind of like a decoder. So the activation verbalizer takes in an activation and produces a natural language explanation of what is encoded in the activation. And the activation reconstructor is supposed to take in that verbalization and supposed to reproduce the original activation. So this is like kind of like a autoencoder, but the bottleneck here is natural language. So here's an example. So we have this rhyming couplet here, and we take the token it and apply that the activation of that token on our train NLA, and we get an explanation. So you can see that like the model is somewhat thinking of like what is supposed to follow that text, and also like thinking about rhyming this sentence. And in terms of training a natural language autoencoder, there are basically two phases. So the initial phase is the warm start SFT phase. So in this phase, what we do is we take our training set, which is just a bunch of text, and we randomly select tokens from that text and extract the left truncation of that token, so that we use a LLM judge to generate explanations of that truncated text. So that is our SFT data. So we independently train both the activation verbalizer and the activation reconstructor based on that summary generated by the LLM judge. And then once we do the SFT phase, then we have the RL phase. So this is basically like a joint training of both the AV and the AR modules. So we feed in activation from our training set, and we do like various rollouts. The AV does various rollouts, and then we do like GRPO to train the AV module based on the reward that is generated by the AR. So we want to we want the AV to generate verbalizations which are faithful, meaning that the AR can correctly reconstruct the activation from the generated verbalization. So basically, that's the main idea. And so one of the results that we have so far is trying to see how robust these verbalizations are in terms of like training configurations. So on the left, you see this tree. We have like these base LoRa adapters, and we branch off based on the LoRa initialization. So we have seed 0 going to the left branch and seed 1 going to the right branch, so that we get two LoRa adapters with different seeds. And then we do SFT on those LoRa adapters. And next, for the RL phase, again on the left branch, you see we have this RL data order. So we have two different branches based on the data order of the training data that we give for the RL phase. So we get seed 0 and seed 1 again on the left branch, so that we get two adapters, and then we do an RL training there for each of these adapters, and we get basically 4 NLAs. And what we did was like we took a pair of AV and AR modules from each of these NLAs and tried to see how good AR from one NLA can recover the activation from the verbalizations of either the same NLA or a different NLA. And the metric that we use to measure the performance is called FVE. This is a fraction of variance explained. So this is just like a R squared measured of regression. So it's 1 minus the sum of the squares of the residuals divided by the this variance term. So y bar is the mean. And you can see that the diagonals are relatively higher than the off diagonals. And this is expected because these are like AV and AR modules for the same NLAs. But even for like different pairs, different NLAs, like the scores are not too low. Like it's pretty good. So basically, this is saying that the ARs, even though we have like different configurations when we train these different NLAs, the ARs still have the capability of recovering the activation from a different AV that it didn't see during training. So for future work, we're planning to do more benchmarking these natural language verbalizations and doing more interventions like paraphrasing or steering and so on. And just want to mention that we have done lots of experiments, and they're all over the place, on various parts of the NLA model. But since we had to choose a common theme, and we did that recently, so that's why we just presented these few results here. But yeah, we still have a lot more to work on. But yeah, thanks.
Okay, so thanks for the nice talk. Is there any question from the audience? Yeah, as usual. Well, maybe some. So if I get it correctly, so once you have these natural language autoencoders in here, you basically have some stability or consistency results, essentially, if I understood correctly, right?
Yes.
So once you have these, what do you do with them? Is maybe a naive question.
Yeah, so what we did was we took the the verbalizations from these various NLAs, and we did a mean pooling of the activations of those verbalizations and we tried to experiment if we can like distinguish two different NLAs just by looking at the verbalizations. So we are doing some kind of like a logistic regression, like a linear probe on those verbalizations, on the activations of those verbalizations to see like if we can distinguish these NLAs. And we did that experiment, and like we have greater than 90% accuracy just by doing like simple logistic regression. We can like distinguish these different NLAs by looking at the generated text. So like what we found was that these different configurations have like certain quirks in that these NLAs learn a specific way to generate those verbalizations. Like one NLA can use like a lot of say like certain words that might not be used by some other NLA, like some structure there that's used by like some NLAs but not others, and so on. Yeah.
Okay, thanks. Okay, if there are still no questions, I think we can move on. So thanks again to the final talk of today. So Project I9, tracing subliminal learning to pre-training. So I think Vishesh, if you are here.
Yep, just sharing my screen.
Ooh, did something happen? Well, it looks like they left, so I'm guessing maybe they had an issue.
Sorry, I just had to rejoin to give permissions.
It's alright, it's alright.
Is my screen visible?
I can see your screen now, yes.
You can? Awesome, okay.
Okay, take it away.
Yeah, so let's start the timer. Yeah, so just talking about subliminal learning, tracing subliminal learning to pre-training. It's me, Angela, and then mentored by Gonzalo as well. So a brief idea on what SL is you have a base model, for example, GPT 4.1 in the main paper, and you system prompt it to have a trait. An example is, for example, you system prompt to like owls. Now that owl-biased teacher model is asked to generate some numbers, and those are benign, unrelated numbers to owls. But again, if you take another base model and fine tune on those numbers, then the base student model also develops that trait. And this is then, and subliminal learning is then said to be successful. So you give the teacher a trait, the student trains on trait-free data from the teacher, and the student still picks up the trait. Now, this is a very normal setting because we often use synthetic data to fine-tune LLMs. And imagine this scenario, and if the main LLM was misaligned, then this would lead to misalignment without the user even knowing. Why and how does this happen? there's been a lot of research previously. For example, some people argue that there are some distinct tokens that are only responsible for that. If you hide those tokens, then it won't happen, which are called divergence tokens. And then some people argue that there's a steering vector that's being learned during the fine tuning of the student. And if you remove that vector, then SL doesn't happen either. And some people argue that it's related to the drift of class and auxiliary heads during the fine tuning or the training of the students. However, no one has given like a mechanistic analysis of the same, and there's no clearer picture of like when subliminal learning succeeds. Is it like a shared initialization or like a shared data order or something else which we are not aware of? And polypythia is a perfect setting for this because we easily can ablate the different weight and seeds initializations and do experiments in those, and then be able to come up with the mechanistic backing of and trace this back to the roots of why it's happening. And no one has tested it on pre-trained models either. So just talk a little bit about that. Everyone has tested this on like instruction tuned or like frontier open source models, which is why one of the challenges was to get even like we weren't even sure if Pythia would even show SL just because of its autoregressive nature and it not being instruction tuned. So dealing with a lot of like log probabilities and it not even generating a coherent number sequences and all that stuff. Happy to dig into it a bit more later if people have questions. Now, the results that we got were interesting. We were able to install a trait in the teacher and the student via like completion only loss, which the main paper does, and also using synthetic document fine tuning, which no literature has previously studied in this scenario, which was pretty cool. And then we also found out that similar data order has a higher trait than a similar weight order, which is also very interesting and counter to the literature that we have currently. And also that something else which was counterintuitive was similar initialization is not even necessary for subliminal learning. It can even occur without the shared initializations, which the current research has argued upon. And another thing is subliminal learning SL is highly fragile to several hyperparameters. So we had to do like massive sweeps to find out the ideal ones. And then another thing which you can see from this chart on the right is also that full fine tuning often excels in installing the trait than LoRa, which is also something the current literature denied because they said that this is a lowering phenomenon for full fine tuning just disrupts it, which was not what we observed. Now, what's next is to dig deep down into why this is happening, leverage representation level similarities to compare why the data seeds, similar data seeds show better SL, and then also tracing it back to like the data that the model saw during fine tuning and running several ablations on that data order during the fine tuning of the student to see how SL emerges, and also to robustify and report in the papers that we will be working on to would be to just like robustify over like more animals, more domains, like for example, code, misalignment, and have just like robust seeds for handling stochasticity is all. Happy to take any questions.
Okay, thanks for the talk. I do maybe have a naive question because so every time I check out what Gonzalo is doing with subliminal learning, I see people talking about like various kinds, so like trying this subliminal learning with different animals, and like I'm very curious, like does it matter like which preference you're trying to induce, or like, or am I misunderstanding what's going on in these chats?
Sorry, could you repeat the question once again?
So I see, at least when I look at like Gonzalo's project, I see them trying not just like one animal, like or like one like preference trait, but like different traits. And I guess so. Is there like a different which trait you ask the model to pass on, or?
So, answering the question, no, there's not a difference. Right now, the category of traits that we have tried as animals, for like we've only tried like cats, dogs, and wolves, since those were like single token and Pythia tokenizer. But even like we're confident that even when we explore like different domains, say for example like plants or flowers or other domains, this would be expected as well. So no, it is not category dependent, if that answered the question.
Okay, yeah. But like between animals, like do you see any meaningful difference between animals, or is it just?
I see. Yep. No, I see. Yes, definitely. There's also a difference in how much the trait is transferred between animals and the mod, and a part of it definitely relates back to how much base Pythia loves animals. One thing which we found out was the base Pythia model loves dogs a lot more, even more than the fine-tuned dog model. So that would not be a robust treatment. A robust treatment would be to have a animal which the base Pythia doesn't love as much and still instill that trait, which is what we also discovered. So just keeping that in mind of like how base Pythia does on these benchmarks, it also does make a difference. And another thing is experiment down the pipeline is to control the number of documents we fine tune on, because that also helps in the aggressiveness of the trait.
Okay, yeah. So basically like bias control, essentially, all of this.
Right. Yeah.
Yeah. Okay, I had another question. I'm trying to find it again because I lost it. Yeah, maybe like if I understood correctly, like a piece of good news is that actually this is a bit of a fragile thing, or like not it's not super that easy to get.
Right. Yeah. Because I think it was just because it was a pain to even get a coherent text generation from Pythia. Like we had to try a bunch of different like prompts, and something which I didn't cover in the slides just because of time constraint was that we are also using a different strategy for instilling the trait, which is also like we're obviously doing the number generation, but we're also doing on policy distillation, and that seems to be much more like the trait seems to be much more evident in those like using just OPD. So there's that.
Okay, nice. Well, so thanks again for the nice talks, and thanks everyone really, because I really enjoyed every single talk here. I think so. Not every group here was represented, but like I think everyone has done some nice progress, and I look forward to what's going to come out in the end. So maybe as a note, so last year a bunch of projects continued past SOAR. Um, Probably that's going to happen for some of your projects as well. So like don't like yeah. Well, we'll see, but hopefully like everyone gets some nice deliverables or hopefully a paper out of it. So looking forward to it. So yeah, so this is now the end of week 3. There's 2 weeks left, so in 2 weeks we'll see each other again. Hopefully with more projects to show. So thanks everyone, and I think we can leave it at that. Unless someone has a question now.
Thank you. Thank you so much for hosting.